Hello statics team, Prof. Joe here. Today we are moving beyond particle equilibrium into the grand wide world of rigid body equilibrium. And I want to start off with a discussion of degrees of freedom and also how you're going to be drawing free body diagrams from this point on. So let's get started. Okay, so what do I mean by equilibrium of a rigid body? Now, we've done a lot on equilibrium already. And it looks like I already had up there. We know that equilibrium means the sum of the forces are equal to 0. And so far, that's all it's meant to us in particle equilibrium. So let's talk about what do we mean by rigid body. Well, the clearest definition is a body that's not deforming. However, we've actually been in rigid body mechanics this whole time. All of statics, all dynamics is all rigid body mechanics. So that's not really telling us anything new. What it's not telling us is more important. We are no longer having a particle assumption. Okay, so we're taking off those training wheels, the idea that all forces are acting on an infinitesimally small speck. We're going to take that away. And what have we learned so far about that? Well, we just learned about moments. We learned that if a force is applied at a distance, it creates a twisting that we call torque or moment. And if an object's not moving, all of those moments have to be 0. Otherwise, it would be twisting. So now, not only do we have the sum of the forces, but we also have the sum of the moments equal to 0. And that is also a vector equation. I'm going to go into that more later as we do our equations of equilibrium. Today, I want to talk about rigid body mechanics. And I'll say here, this is really, we're just getting no more particle. Okay, so our particle assumption is gone, which means we have to draw the full body and we have to draw forces where they're acting. We also sneak one more thing in there. Up to this point, we have basically told you where the forces are acting, except for weight and ropes. You have already used your knowledge of physical situations to put the weight in the center of gravity, and you've used the fact that ropes cannot push to change a rope that's connected to something to a force. We want to build on that. We want to build your skills at making free body diagrams. The main reason is, as an engineer, you're not going to be told what forces are acting where. You have to look at a physical system and then draw a mathematical model that represents that system. And that's what we're going to practice as we move into rigid body equilibrium. And as you move into replacing physical systems with the forces that they create, it's important that we talk about degrees of freedom. I'd also like to talk briefly about strategy. I encourage you, do not memorize the supports and the forces that replace them. Instead, you need to understand and apply how physical systems can be represented in forces. What do I mean by that? Well, if you just memorize the images in the textbook, what happens if I give you a different type of image? Or, more importantly, when you're in the field and you see two pieces of metal connected together in a new way, how are you going to apply the knowledge that you gained if you haven't practiced applying it to physical situations? Let's first talk briefly about degrees of freedom. What do I mean by degree of freedom? It basically means how something can move. Okay, so if I grab an object, say I have this socket, how can I move it? Well, we're going to start off in 2D. And in 2D, we can only move either right and left. That would be 1 degree of motion. I can move up and down. That would be another degree of motion. Or degree of freedom, sorry. I can move right and left. I can move up and down. And I can twist. That's where this getting rid of the particle assumption comes in. Okay? So in 2D, we really have 3 degrees of freedom. You can go back and forth, up and down, or twist. And what we want to do when we're looking at supports is we want to ask ourselves, how many degrees of freedom does this support restrict? In other words, how many degrees of freedom do we know it's not moving in? And then we're going to have to talk about static determinacy, whether our object is actually in a situation of equilibrium. But let's move on to a few supports. The most common supports you're going to see, we're going to start off with some of the most common supports you're going to see. The first one is a roller support. Okay, here's an image from the textbook, but let's talk about what that really means. A roller support is, let's say we had a bridge this 2x4 will be the bridge, and we had a roller. Okay, so this roller is on the end of this 2x4. We have to ask ourselves, what degrees of freedom does this restrict? Well, first off, can I go back and forth? Yes, I can go back and forth. The roller's not restricting that. It would just roll. There's nothing keeping me from going back and forth. So that is not restricted. Okay, then I ask myself, can I go up or down? Well, I can. I can go up. Can I go down? I can't go down. When it hits the roller, that roller would be on a rigid surface and it would not allow it to go down. Can I twist? Yes, I can twist. It can move. So which degree of freedom does this restrict? It only restricts one degree of freedom, its ability to move downward. So what do we do to replace this support on your free body diagram? Well, if we have that 2x4 drawn as an object here, we're going to restrict it from going down. I'm going to put an arrow up. I now have one unknown, and if this was at point A, I would call that AY, because it's going to restrict the motion in the y direction. A couple of quick reminders. One is that I draw the body free, and I make sure I make an outline of the body. Now, what do I mean by drawing it free? Well, it's not technically correct if I were to leave that support in here, right? If I were to draw something like this with the support and an AY, well, that's not a free body. I left the support in there. The idea is you replace the support with a force. Okay? Let's move on to some more common support. The next most common support is a pin support. Here's a picture of a pin support on an I-beam. That's from the textbook. However, you see pin supports all over the place. I can grab things out of my drawer that have pin supports. Here are some scissors. You can see that the pin support allows them to rotate, but I can't pull it up and down, and I can't pull it back and forth, but it does rotate. Very similarly, on my shears, it's in a different location, but that's still a pin support. Another pin support would be an example of this breaker bar. You can see there's a pin support on the end here. We're currently in 2D, and that pin support is only going to rotate in and out of the page. When we get to 3D, we'll talk about what happens when it's in different orientations. So let's look at a pin support. Does it keep me from moving right and left? It sure does. I can't move right and left. I can pull and pull. It's not going to move. Does it keep me from moving up and down? It sure does. I can't move up and down. So it restricts those 2 degrees of freedom. But does it keep me from rotating? Nope. A pin support is made to rotate. So when we replace the pin support, we would end up drawing that body. We're going to remove the pin support, and we're going to replace it with a force in the y, which we'll call AY, and a force in the x, which we'll call AX. 2 forces because it restricts motion in 2 directions. Now, when you think about it, you're going to end up with a single support reaction. We just don't know what angle it's at. So when we actually solve for this, we're going to have a single force at A, but it could be in any direction. Right, this might end up being our A. And we don't know if it's in that direction or up or down. So we don't know its magnitude or direction. And that's why we represent it with an AX and an AY. If we know those 2 components of our vector A, then we're going to know both its magnitude and direction. So this gives us 2 unknowns with this pin support. And the final common support we're going to talk about today is a fixed support. A fixed support is made so it's not supposed to move at all. It's not supposed to move in the X and Y, or it's not supposed to move in the X and the Y, or rotate. You could picture a fence post in cement, or a couple of steel beams welded together. They're made to not move in any direction. So we have to restrict all 3 degrees of freedom. So we're going to take the beam out of the wall, make it free, and then we're going to restrict the 3 degrees of freedom. If this was at point A, we're going to restrict our AY, we're going to restrict our AX, and we're also going to restrict it from rotating. So we're going to add a reaction moment. I always recommend just drawing the moment in the positive direction using your right hand rule. And then when you solve for it, if you get a negative number, you know it's in the opposite direction. Okay, so there's our 3 most common supports. Let's look at some other supports you might see. Another common support you might see is a rope or cable, and we've already talked about this one. A rope always has to support the load in the direction of the rope. If I have my right hand here and I'm trying to pull my left, if I push up, it's not doing anything. The only way I can pull my hand is along the rope. If I move the rope this way, it's still along the rope. The force has to always be in the direction of the rope. I can't move it up. I also can't push. My right hand cannot push my left hand. Right? The only way is by pulling. So the force always goes along the rope and in a pulling direction. So if we have a drawing such as this, we know that the force only has one unknown, not 2. And that unknown has to be in the direction of the rope. So that gives us the direction of our reaction support vector, but not its magnitude. So how are we going to do that? Well, we'll draw whatever the object is that it's going to be pulling on, and then we would take away the rope and we replace it with a force that's going in the same direction as that rope. So I want to make sure that my theta is known and drawn on the picture. Right next to it, you'll see what's called a weightless link. And this is actually a two-force member that you're going to learn a lot about as we continue on a rigid body equilibrium. What a two-force member means is it's a member that has pin connections at both ends. Okay, so if you picture this pen having pin connections at both ends, if I were to try to push my hand back and forth, it would just twist. Okay? If I were to go down, it just twists. The only way that I can keep it from moving is if I either push or pull. Push or pull. So it's very similar to a rope, but it's a rope that can push. So a weightless link, we're going to do a very similar thing. We're going to draw the body it's acting on, and we're going to draw a force acting in the same direction as that weightless link. Make sure to mark our theta on there. Now, whether it's an arrow pointing up or an arrow pointing down, that will depend on the situation. I recommend putting it in one direction and then staying consistent. When you solve for the magnitude, if you get a negative number, well, you know that your direction was wrong and that it's actually pulling in the other direction. Additional support reactions you might see. A roller support. Now this is exactly like the roller support we saw before. These are just some different pictures that are pretty much doing the same thing. The one on the left, you can see that there kind of looks like a pin support, but be really careful and look at the image. If you look at the bottom of that pin support, it has little wheels on it. It looks like a roller skate. That's meant to be a roller support. How do we do a roller support? Well, we're going to, just like we did with the previous one, we'll take away the support and we're going to give it a single force that's perpendicular to the surface that it's acting on, because that surface can only push back perpendicular to itself. And we're going to have one unknown because the surface is going to tell us what direction that force is on. Very similar to the one next to it, like a bearing inside a sleeve. Now, the only thing about that is it could pull either up or down. Okay, so you're going to pick one direction and stay consistent. You're going to have the same drawing. It's going to be perpendicular to that slot that it's going in. And finally, we have a slightly more complicated one. This one, hopefully you can picture a tube or a sleeve, and there's a rod inside of it. So that sleeve could actually slide up and down along the rod. Now we have to ask ourselves, what degrees of freedom is it restricting? Well, if we just look at x and y, it gets a little confusing because if I pull in the x direction, would it move? Yeah, it would move a little bit. It could slide up and down that rod. So we actually have to tilt our coordinate system, and we would say, okay, well, for this one, I'm going to draw the body. Let me draw it over here where I got a little bit more room. I'm going to draw the body. It looks something like this. Okay, and now I got to tilt my coordinate system, and I say, well, if I try to move it perpendicular to that rod, it's not going to move. So I need a support reaction there. So I'm going to put, we'll just call that A. And then we know what direction that's going in because we have the direction of the rod it's sliding along. Okay? If we were to go perpendicular to that, it would just slide along the rod. So there's only 1 degree of freedom in translation. But how about rotation? Can I rotate this? No, if I tried to rotate that, it wouldn't go. So I have to make sure that I have a moment reaction as well. and I'm going to draw that moment reaction in the positive direction. And then I'm going to use my equations of equilibrium to figure out if the magnitude is positive or negative. So my suggestion to you here is don't try to just memorize that table. Don't try to just memorize this picture means that reaction. Instead, try to ask yourself, what degrees of freedom do I have and which ones are restricted? Being able to translate the physical reactions in the real world into a free body diagram, that's one of the biggest things you learn in statics. So I really encourage you to work on it. Let me know if you have any questions.